Good afternoon. Welcome to the afternoon session. It's a pleasure to have Professor Stefania Gori from the University of California, Santa Cruz. Professor Gori has, of course, had a very distinguished career. Among other notable achievements, she has the National Science Foundation Careers Award from the US, and also I'm very pleased to say the award-winning paper for Frontiers of Science award in particle physics and phenomenology for this year at the ICBS. So please, Professor.
All right. Yeah, thank you. And yeah, this talk is going to be about neutrino physics. So let me start with a little bit of a historical note on neutrinos. So we started thinking about neutrinos almost a century ago in the context of beta decays. So back then, we were trying to explain why we have a continuous spectrum of electrons from beta decays. And this could only be explained if there were these particles that later on were called neutrinos by Fermi. Neutrino discovery came a couple of decades afterwards. These were reactor neutrinos that were interacting with matter, creating positron, and then positrons were annihilating with electrons, giving the final state. A few years after, we started thinking about the possibility of having neutrino oscillations. This is the period in which actually we were discovering other type of oscillations like kaon oscillations. So Pontecorvo had this idea of having perhaps also neutrinos that were oscillating. And then afterwards, we had also the muon neutrino discovery at Brookhaven, where muon neutrinos were produced through pion decays. And after all these discoveries, we started to have actually problems. So the first problem was the solar neutrino problem. Namely, we started seeing that the sun was sending us, or we were receiving less neutrinos from the sun than expected. Similarly, in the 80s, we had this atmospheric neutrino anomaly, namely, we were receiving less muon neutrinos from cosmic rays compared to what we were expecting. And only in the late 90s, we discovered neutrino oscillations at Super Kamiokande. Afterwards, again, another discovery, namely the tau neutrino discovery by the donut experiment at Fermilab. And then we had confirmation of neutrino oscillation, either solar neutrino oscillation or atmospheric neutrino oscillations at Sudbury or K2K experiment. So this is a little bit of a summary of problems and discoveries in the context of neutrino physics. And we have to keep in mind for later the rest of this talk that most of these discoveries were done using the charge current interactions of neutrinos. So the fact that the neutrinos interact with the W boson and the charge lepton. With the exception of this discovery here, so at Sudbury, so what scientists were doing was to measure the absolute number of neutrinos, and this was using also neutral currents. Okay, so already from here we see that perhaps we know less about the neutral currents of neutrinos than charged currents, and we see that this is indeed true. So in the context of neutrinos, we have a lot of open problems. So perhaps one of the main one is the origin of neutrino masses. So if neutrinos are Dirac or Majorana, so if they are their own antiparticles or not. Then we don't know also if neutrinos violate the CP symmetry. What are the neutrino masses and mixing angles, if we have this inverted or normal hierarchy. And so these are problems just concerning neutrinos. And then perhaps neutrinos are also related to other open problems in the open problems in particle physics, as the baryon-antibaryon asymmetry of the universe, or perhaps dark matter. As we know, stellar neutrinos could be, in principle, a dark matter candidate. So let me spend a couple of words on a couple of these problems that I just mentioned, so that then we connect to the rest of this talk. So I already mentioned that we don't know what is the origin of neutrino masses. And in particular, there are two possibilities, either Dirac or Majorana. And if they are Dirac, as we also heard this morning, then we need a Yukawa coupling that is super, super tiny. For Majorana, we can have, seesaw mechanism that more sort of naturally leads to tiny neutrino masses that are much smaller than the masses of the other standard model fermions. What is interesting in this context is that we have many experiments that are trying to disentangle between Dirac and Majorana. And in particular, we are looking for neutrino-less double beta decay. So this process here, where we are converting two down quarks into up quarks and producing two electrons without any neutrino. And this process happens only if we have a Majorana neutrino. And if we discover this process, we are going to see a ME that is defined here that is non-zero. However, this, as we showed in a recent paper, this is not the only way. So there are other combinations of neutrino masses and PMNS matrix elements that could tell us if neutrinos are Majorana or not. So all these combinations here, if non-zero, would tell us that indeed we have a Majorana neutrino. Okay. So this is one problem that I wanted to mention. This is related to some BSM physics that we see later in this talk. And the other problem that I wanted to mention is are the values for neutrino masses and mixing angles. So first of all, we don't know if neutrinos have this normal ordering or inverted ordering, where we have here two neutrinos, the two lightest neutrinos that have a small mass splitting, or the two heaviest ones. And then also, here you can see the latest measurement of the several angles in the PMNS matrix and the several mass splitting. And we see that these values are not that precise, and even less precise is the measurement of delta, so this possible CP violating phase, and basically we have no idea what the value of delta is. And there is a large neutrino endeavor to try to measure this phase. So what is this trident process that we consider for our paper? So as I mentioned at the first slide of this talk, so neutrinos were discovered using, obviously, weak interactions, and in particular, the interactions of neutrinos with the W boson. So these are the charge current interactions that we see here. And so neutrino trident production is this process that we see here. So it's the scattering of neutrinos versus matter, and then we are extracting from the Coulomb field of the nucleus two muons. There are two Feynman diagrams that are contributing to this process, either the exchange of a W boson, or we can put also the Z boson. So this neutrino trident is probing the full weak interactions, not only charge currents, but also neutral currents. And this neutrino trident has also a long history that I'm summarizing here in one slide. So here I'm starting very much in the past with the first idea of weak interactions by Fermi, this 4 Fermi interaction. Then, okay, there are a few more discoveries, the discovery of parity violation, the theory by Gelman and Feynman, the V-A theory. You see that already pretty much early, people started thinking about this neutrino trident production already in the 60s and 70s, either in the V-A theory, so the theory with only the W boson, or the full weak theory, the theory by Glashow, Weinberg, and Salam. Then we had indeed the discovery of the weak interactions, either indirectly at the Gargamel experiment at CERN, or directly. We had the discovery in the early 80s of the W and the Z boson. And only in the 90s, we started to look for this trident process that was actually considered theoretically in the 60s and 70s. And these were the experiments that tried to discover this process. So CHARM2, CCFR, and NUTEV. These experiments, so these searches for neutrino trident were almost forgotten. And then we started to get curious about this trident production in 2014 when we brought our paper. And actually, a lot more people started to consider this production. And indeed, this CCFR paper here started to get a lot of citations after 2014. So let's see what we can learn from this trident production. How do we compute this process? So these are the two Feynman diagrams that I already mentioned a couple of slides ago, either with the W or the Z-boson exchange. And so one approximation that we can do in order to write down analytic expressions is to use this equivalent photon approximation. So what we do is basically to cut the diagram here, and so we are connecting this 2 to 4 process to a 2 to 3 process where we are scattering neutrinos versus photons. Now, this approximation is only valid in the approximation in the hypothesis that the momentum exchange here, Q, is relatively small, so we have a photon that is almost on shell. And then, of course, we have to weight this cross-section with the probability to produce, to have this photon with a certain level of off-shell, so with certain amount of Q square and some center of mass energy S. Okay. Here you can see that this process is enhanced by the second power of Z, Z of the nucleus. And then also it depends on the electromagnetic nucleus form factor. And these are very well measured, as we will see. So this is an approximation that we don't necessarily need to do, but this is something that we can use in order to have analytic expressions for this process. And then we can compute this 2 to 3 process here. What we can do is to integrate out the W and the Z boson in order to have this effective Hamiltonian. And then we can compute the cross-section for this 2 to 3 process that, as we can see, depends on both the vector coupling and the axial vector coupling, as well as is enhanced by the center of mass energy S. Okay. If we do this calculation, what we'll see is that we get a cross-section that is several orders of magnitude smaller than the charge current interaction scattering cross-section of neutrinos. So we are talking about a process that is pretty much suppressed in the standard model. Okay. This, as I said, is a calculation just in the context of the standard model, but perhaps neutrinos interact with some additional new physics. Perhaps they interact with new gauge bosons. And new neutrino interactions have been used actually to explain the pattern of neutrino masses and mixing angles. In particular, there are a lot of papers by now on the possibility of having neutrinos interacting with this mu minus L tau gauge symmetry. So what we do is to take a global symmetry of the standard model and to gauge it. And this has been used to explain why we have a theta 2-3, this mixing angle in the PMNS matrix that is nearly maximal, and also why we have a mass splitting that is much smaller than the other mass splitting. So this is a pretty simple theory. We have the standard model plus these interactions of the new Z prime. And we see that the Z prime interacts with muons, taus, as well as neutrinos. What happens to the trident production? Right here, I'm just saying that this symmetry has been used also for other reasons, in particular to address some of the anomalies in data and also to construct dark matter models. So what about neutrino trident production? Of course, if we have this Z prime, then this Z prime will contribute to this process. And then we get, in general, an enhancement of the cross-section. We see that this contribution here is always positive. And so this equation here is valid only if prime is quite bigger than the center of mass energy. Otherwise, we have a different type of behavior, and we can have also some destructive interference. And then what we can do is to compare this with this old experiment, so this CCFR, CHAM2, and NUTEV. So what are the experimental results that we are comparing to? here I'm summarizing what these 3 experiments were telling us. So the first observation of this trident production was claimed by the CHARM2 experiment at CERN. This was using something like a 20 GeV neutrino beam on a glass target, and this caused several events, as we can see here. Then the observation was sort of confirmed by the CCFR experiment, where they were using a much more energetic neutrino beam. And if we look at these cross sections that were, so these numbers that are coming from this from the CCFR paper, we can see that CCFR taken at face value was able to demonstrate that we have this WZ destructive interference. Because if we consider only the W boson exchange, then we would have a cross section that is much quite bigger. Okay. And then the last experiment, NUTEV, didn't give us any conclusive evidence for the trident production. Okay. So here I'm summarizing the experimental result. So this is the ratio between the cross-section measured and the standard model cross-section. And however, things are a little bit more complicated than this, because actually in the NUTEV paper, there was a claim that the CCFR investigation was not that solid. In particular, apparently, CCFR was missing to identify an additional source of background. This was coming from the production of a D meson that is giving us a muon in the final state, and then also there was some mismodeling in the signal. So reading this old paper by NUTEV, it's not really clear if the observation was a solid observation of this trident production or not. And this gives us even more motivation to look for this process at future neutrino experiments like at DUNE or hyper-K. Okay. But in the rest of this talk, what we'll do is to take at face value these results and see how far we can go in physics, and then also we'll investigate what we can do at DUNE, at this future neutrino experiment. So here you can see the parameter space of this theory, where you have the mass of the Z prime and this coupling constant G prime. And here you can see that this gray region here is what we can probe, taking this result by CCFR. Okay. Also, what I'm showing here in this plot is the G-2 band. This was taken from this old paper, so things, as we know, are not really clear if there is an anomaly and how big it is. But just to draw our eyes, here is the G-2 band as a few years ago. And then also what you can see is what were the other searches for this type of theories when at the time of writing our paper. So back then there was only this search for Z going to 4 muons that was able to constrain some region of parameter space. That, however, we see that is pretty much limited in terms of the mass range. Okay. All right. Now the question is, what can we do in the future? And in particular, we'll have 2 very big neutrino experiments that are DUNE and hyper-K. And we know that the neutrino intensity, the intensity of the beam will be much bigger. At the same time, DUNE will have a near detector with a value of Z that is smaller than the value of Z at CCFR. So we are going to lose a little bit on cross-section, and also smaller neutrino energy. And we'll see that having a smaller neutrino energy will pay the price for the cross-section. And here in this plot, what I'm showing is the same plot as before, where we see the CCFR region above here. And then I'm showing what regions of parameter space we would be able to probe if we had the measurement at a level of 10% or 30% at DUNE. Okay. And we see that measurement at a level of 10% would be able to completely close this G-2 region. Or in general, we would push the sensitivity to coupling constants that are something like an order of magnitude smaller than what perhaps we were able to probe with CCFR if, again, taken at face value. Right. Also, what is interesting is that if we are in the regime in which the mass of the Z prime is much bigger than the center of mass energy, then we have a linear dependence, as we see here on this line. And then this linear dependence actually goes down to lighter masses at DUNE if compared to CFR, because as we said, at DUNE we have a smaller neutrino energy. So in general, we expect that even having a 30% measurement will help us probing additional regional parameter space if compared to CFR because of this linear dependence. Okay. There is, here I want to mention that there is a big endeavor in trying to search for new physics at present and future neutrino experiments, in particular at near detectors. So there are two ways of probing new physics at neutrino near detectors. One is shown here. So basically the idea is to produce the neutrino beam that is scattering with a near detector, and then measuring the several processes here, we can indirectly discover new physics if we see a deviation of the cross-section of whatever process if compared to the standard model. And this is precisely the case of the trident production, that we are measuring a cross-section and then we are trying to see if it fits the standard model prediction or not. And then there is also another way, because here we see that basically we have the neutrino experiments are initiated by a proton beam. This proton beam produces pions that then produce the neutrino beam. But in principle, we could also produce some new particle here, as for example, dark matter. And then we could do scattering experiments in the near detector if we have some new particle that we are producing. Okay. So there are these two complementary ways of probing new physics at neutrino near detectors that are very important. And here I'm showing a cartoon of the DUNE experiment, where we see here that at Fermilab we have the near detector. And similar arguments also apply to Hyper-K in Japan. So going back to our trident production at DUNE, so what we did in this follow-up paper was to investigate the capability of the experiment to probe, indeed, this trident production. So to see if we can reach this 30% or maybe even 10% measurement of this trident production. And so we did the calculation for both the coherent process and the incoherent process. So basically, we are computing the neutrino scattering with a full nucleus or just against a single nucleon. And we can see that the coherent process is enhanced by z squared, as we saw before. Instead, this incoherent process scale with the linear power. Okay. In the calculation, we see that we have the dependence on form factors, in particular the electric form factor or the electric and magnetic form factor here. And then also we see here that we have dependence on the Pauli blocking for the nucleus. And here we see that I will comment that this is the main source of uncertainty in the calculation of the incoherent process. And in fact, what are the theory uncertainties in this calculation? So the coherent process is pretty well known. So the main uncertainty is coming from higher order electroweak corrections. For the incoherent processes, instead, we have larger uncertainties that are mainly coming from here, from this Pauli blocking. Okay. And we estimated that to be at around 30% or so. Now, what is the prediction for the cross-section? So here we see the cross-section in femtobarn. Looking at these numbers, we can see that it's pretty small. And we see that we have a large dependence on the neutrino energy. So it goes pretty much down if we take a neutrino beam that has low energy. And so here we see that we pay the price for at DUNE if compared to past experiments like CCFR and CHARM2. However, as we see, we can have a good reach because DUNE will have a much more intense neutrino beam. So we did the calculation, and you see that these three lines here correspond to the prediction for the coherent and incoherent processes. The incoherent processes indeed are subleading, as we would have expected, because also they scale with a linear power of z versus the second power for the coherent process. And here we see the number of events after basically 3 years of run of DUNE. And we have a number in the multi-hundred of events. So we can have quite a bit of hopes of perhaps seeing this type of process. And also, as a byproduct, what we did was to write down a source code for the generation of this trident production. So a code that is computing both cross sections and also distributions for the muons, so that it can be used directly by experimentalists or theorists as well. And then in our analysis, we had to consider what are the backgrounds to this process. And there are a lot of backgrounds, actually. It's very frequently at DUNE, we are producing a muon and a pion. And this is very similar to two muons in terms of signature. So we see that the starting point is not that good because we have a huge amount of background. So this is very frequent, as I mentioned. But then using kinematical variables, we can quite a bit disentangle between the two. And this is coming basically studying the length of the tracks as well as the opening angle. So what happens is that muons usually leave a longer track in the near detector of DUNE if compared to pions. And this is what we see here. So here you see the background that is falling pretty quickly for the length of the tracks. Instead, the signal has longer tracks in general. Also, we see that there is a bigger difference between the length of the two tracks for the signal if compared to the background. And then finally, we have the background will have a larger opening angle between the two tracks if compared to the signal. So this to say that there are kinematical handles that we can use to disentangle between signal and background. So we can optimize on this and then find the result that is relatively good in terms of seeing this process. So bottom line is that we expect to have a signal of a square root of background at a level of 1 per year. And therefore, it's something like a 40% measurement after 6 years of run. So this, of course, is not, we cannot switch on DUNE and see this process, but this is something doable. And especially in the context of having past experiments that don't tell us for sure if they saw the trident production or not. So it will be really important to see this process at DUNE. Okay. So having this in mind, then we can constrain new physics. First, we can write down some effective interactions of neutrinos with muons. So these dimension 6 operators. So these operators come in the standard model, but we can have an additional contribution. And then we see what type of parameter space we can constrain. Again, in gray, we see the CCFR taken again at face value. And then here we see a 40% or a 25% measurement at DUNE, what type of regions of parameter space we can probe. And in terms of this L mu minus L tau theory, this is the level of constraint that we can get with a 40% precision measurement. And we see that, again, we can access new regions of parameter space on top of CFR at face value. Okay. All right. Then the question is, of course, what other experiments can do. This is a model-dependent question. And after our paper, a lot of searches have been performed at different type of experiments, both at high energy and high intensity. Here I'm highlighting what is new and what is not. In particular, there are new searches at LHC for this L mu minus L tau theory, new searches at B factories as well as at beam dump experiments. And then on top of this, we have neutrino experiments and in particular boric sequence, as we will comment. So what type of searches we can do? So this is the plot that I already showed you. So this was the search for a Z going to 4 muons by Atlas that was available when we wrote down our paper. And after our paper, there were new searches for this, even for a W decay to a Z prime and the muon and the neutrino, giving a 3 muon plus a neutrino in the final state. And these are, again, the regions of parameter space that LHC was able to probe. Okay. And here for comparison, again, I'm drawing the DUNE and CCFR regions. Then what we have are B factories. In particular, we can do a search for 4 muons also at B factories. There was an old Babar search that I'm highlighting here. And actually, by now, there is also Bell2 search that is giving us a similar reach. You can see it here. Okay. And also, you see that this search cuts here at 2 times the mass of the muon, because the Z prime, of course, cannot decay anymore to muons. And if we are below here, what the Z prime will do is to decay to neutrinos. And by now, there is also a search by Bell2 of the production of a Z prime with 2 muons, and then the Z prime is decaying to 2 neutrinos. And we see here that at higher masses, they are not too much worse than the visible search, but then it keeps going at lower masses. Okay. So these are all new searches, and also there was a new search at the beam dump experiments at CERN. So this is an experiment that is called an A64. So what this experiment is doing is to use a high-intensity muon beam versus a target. And then what they do is to measure the muon beam after these collisions. And basically, if we are producing an invisible particle like a Z prime, then we'll see some deviation of this muon beam. So we'll have some missing energy and momentum type of signature. So this is happening through this diagram here. And NA64 actually was able to set a very interesting constraint on this model. And we can see it here. And this goes to very, very light masses. Okay. So this is very interesting because this type of models really motivated many new different types of experimental searches. And also, we can reinterpret neutrino measurements in terms of this mu minus L tau theory. So what we can do is to take Borexino data. So Borexino is measuring the scattering of neutrinos versus matter. And so if we have this Z prime coming from this mu minus L tau theory, we can contribute to this scattering at 1 loop level. So in this minimal theory, the Z prime will mix with the photon of the standard model and induce this process. And then reinterpreting Borexino data, actually we can constrain the entire parameter space here above. So as we can see, so by now these type of models are pretty much constrained, much more than when we wrote our paper. Perhaps DUNE will have the reach on additional parameter space, because we have to keep in mind that this was a pretty much conservative analysis that we did. So even by now, what we know about the near detector is much better than what we were thinking that it would have been. So and there is the possibility that the near detector will be magnetized, and then it will be much easier to disentangle between signal and background. So what I'm saying is that this blue line can go quite below, perhaps, thanks to this discrimination between signal and background. So it will be really interesting to see this search at the future neutrino experiments. Right. Also, before concluding this talk, I wanted to mention that what we have discussed is this trident production with 2 muons in the final state. But we can compute all trident productions where we have 2 leptons in the final state. It can be either electrons or a combination of electron and a muon. These processes can have a bit larger cross-section because only one diagram is contributing, so we don't have this destructive interference between the W and the Z. And in fact, looking at the number of events at DUNE, we can see that this electron or electron-muon production has a quite large number of events if compared to the 2 muon production. And here we can see again the cross-section as a function of the neutrino energy. Here we can see also that the invariant processes are even more suppressed. So it will be interesting to see what future neutrino experiments can do for this additional trident production that has never been looked for before. And also in terms of tridents, after our paper, there have been a lot of investigation about what people call dark trident. That is sort of the same process, but we are replacing a dark matter beam. We are replacing the neutrino beam with a dark matter beam. And then we have the same type of signature with 2 leptons in the final state. And this was proposed a few years back, and by now there is a search in microBOON. And we see that for this particular model where we have a dark photon, microBOON was able to probe quite a bit of regional parameter space using this dark trident production, right? So this leads to my conclusions. So in this talk, I wanted to give you a few messages. So the first message was that most of the information that we have on neutrinos is coming from charge current interactions. So it's very important to understand better and measure better the neutrino current, the neutral current interactions of neutrinos. The trident processes are interesting, and we know just a little bit about that, about these processes from old experiments. So it will be interesting to see what future experiments can tell us about trident production. And in this context, the trident production can be a good test for new physics models. And there are quite a few processes that we can look for at future experiments and in principle discover these new processes. All right, thank you.
Can you probe anything like that with phaser?
I think you had the paper a couple of weeks ago.
So with higher energy, you have hundreds of JB, maybe TeV neutrinos. So the cross section for the neutrinos, the cross section is much higher. Do you expect at least a handful, maybe 50 events or so, if I remember correctly, at phaser? Again, the question is, can you distinguish it from backgrounds? And probably yes. So we looked at this, and probably you can detect this thing at phaser 2. At phaser 2, when they have the larger detector.
But yeah, as far as I understand, the number of events at DUNE will be much bigger, and
right.
With better prospects of testing this type of models. But
yeah, I mean, the question is how well one can control the background.
Yeah, this is the key, obviously, yes. Yeah.
The constraint of the Z prime and U minus tau. So I suspect there are also some constraints that are coming from lab, no?
Yeah, very good. So I didn't. Yeah, absolutely. So you have at one loop, you are affecting the Z coupling to leptons. Yeah, we studied that in the older paper. Here I'm not showing the constraints, but it is inside this gray region here. But yeah, there are absolutely left bounds. Yeah.
You know how to scale at FCCEE?
Very good. We didn't do the exercise. I remember that at high mass here, at a certain point, they were not too different from LHC. So it can be that there is something that we can probe down here, but also LHC will, improve this bound. So it's a good question. One should look into it. Yeah.
So in terms of these landscape plots, do you have an idea of what the consequence is if G minus 2 isn't an anomaly?
Yeah, so then this green region here would go away. So this doesn't give us any sort of prior on the parameter space, just based on anomaly. If the anomaly is there but is a little bit smaller, then this region here will go down. So yeah, that's the answer. Then I mean, I didn't talk about it, but it depends on the prior that one put on the parameter space. I think in my opinion, it's interesting to probe in general parameter space as long as it is open. There are, papers that are using this Z prime as a mediator between dark matter and us. And then this coupling cannot be too small if one wants to have, for example, a freeze-out mechanism for dark matter. So this would give us a different prior on the parameter space, something that we can aim for at experiments. Yeah.
So G-2 itself can't put a constraint, another constraint onto the parameter space?
Oh, sure. Yeah, it can also put a constraint. Yeah, that's absolutely. So yeah, when we wrote our paper, so we also computed the constraint, and this is inside this gray region. But yeah, absolutely. Then it depends how strong the constraint is. But yeah, absolutely.